So today what we're going to be looking at is numbers in the complex plane, mainly what we call our I tables. Now our I tables, what we've got here is I've got I up to the 20th power. We're going to know something very special about that. Remember, if we know that I is equivalent to the square root of -1, what we know is that when I multiply I times I, I'm going to get the square root of -1 times the square root of -1. Or when I put those two together, that is the square root of -1 times -1, which is the square root of -1 squared, or -1. So I'm going to get a -1 value in there. I itself is just going to be I. So I have -1, and if I multiply that times another I, I'm just going to get a negative I. And I to the 4th is I squared squared, so what is -1 times -1? I'm going to get a +1. So far, so good? Well, if I keep adding the square root of -1, multiplied times itself again and again, here I have I to the 5th. Well, I know I to the 4th is 1. I know I to the 1st is I, so 1 times I is I. I to the 6th can be broken down into I to the 4th, which is 1, and I squared, which is -1. So in essence, I have 1 times -1, which is -1. I to the 7th, again, it's just I to the 4th, which is 1, times I to the 3rd, which is -I. So 1 times -I is going to be -I. And I to the 8th is just I to the 4th times I to the 4th, which is 1 times 1, which is 1. And then at this point, we should notice that there's a pattern going on here. Our I tables repeat. I have I, -1, -I, +1. I, -1, -I, +1. Or if you want to look at it as every other, have I, -I, I, or I could say -1, +1, -1, +1. Cool. We've got a pattern here. Every 4th I value creates a pattern. So I know the number that comes after +1 is I again. Then I know it's going to be a -1. Then I know it's going to be a -I. Then I know it's going to be a +1. In which case I repeat the pattern. I, -1, -I, +1. I, -1, -I, +1. Boom. And so our I tables are going to really help in understanding what happens when we start multiplying by numbers. So down here, basically all we have is we have no more than, I think, I to the squared. But let's go ahead and take a deeper look. So when I distribute an I amongst anything, I'm going to distribute it just like I would a normal number. I would say I times 5 is going to be 5I. The big thing that happens here is when I multiply it, I'm going to get plus 4I squared. And as we've just discussed, what is I squared? -1. So it's actually 5I plus 4 times -1. So 5I minus 4. And then the last thing that we need to pay attention to is lateral numbers or complex numbers are always listed in what we call A plus BI format. We always list the real part first and then the lateral. So I'm going to say, okay, my real one is -4. My lateral one is 5. So I'm going to say -4 plus 5I. There we go. So for number 3, I'm going to do the exact same process. I'm going to distribute my 5I to both these terms. And I'm going to get a 50I minus 60I squared. I know I squared is -1. So I'm going to get 50I minus 60 times -1, which is just 50I plus 60. And then I'm going to write it in the A plus BI format, which means I'm going to list this number first, 60, and my 50i second. And that's it. That's really all that's involved with multiplying i's, even if it's as complex as binomials. If I have this, I'm just going to distribute each term. 2 times 3 is going to give me a 6. 2 times I is going to give me a 2i. I times 3 is going to give me a 3i. I times I is going to give me an I squared. Now the cool part is when I multiply two complex numbers together, because this is really one complex number, I'm going to end up with one complex number. My i's combine, I get 5i. This is going to turn into a -1. So I'm going to end up with a 6 plus a -1, which is just going to be a 5. So I have a 5 plus 5i as my answer. Awesome. And so what I want you to try and do is I want you to try number 7 on your own. Pause the video, knock out number 7, resume it when you're done, and see how you did. Okay, so what you might have noticed is that number 7 is a little different. Same process, but something cool happens. I multiply this positive number times this positive number, or this complex number times this complex number, and I get a 100 minus 10i. And then when I multiply this, I get a plus 10i minus I squared. I notice my two complex numbers cancel out. My two lateral aspects go away. And what I'm left with is I know that this I squared, that's 100 minus -1. That actually turns into 100 plus 1, which is 101. And there's a cool mechanic behind that, and it has to do with how we actually multiply number lines and the visual mechanic of what's going on. What we have right here is that if I were to, let's say, multiply a number like 2 times 3, they're both in a singular direction on the number line, with 0 being over there. I would say, okay, I'm going to go 2 groups of 3. So 3, 3, and I'd end up at 6, because they're both heading in the same direction. Now, with my complex numbers, basically what we're doing is we're going off the number line. If I have my real axis and I have my lateral axis, I know if I go 10 plus I, there's my first number, 10 minus I, there's my second number, I'm going to end up multiplying my two real aspects, 10 times 10, I'm going to get 100, and my two basically lateral aspects are going to cancel each other out. Part of it's going up, part of it's going down. They're going to completely do away with each other. And I'm going to end up back on the real axis. So we'll get more to that in a future lesson, but just to show you that when we multiply complex numbers, we're really dealing with more of a vector system. But let's move forward. Let's try this one again. For this one, when I distribute, I get a 12 minus 6i. When I distribute my lateral aspect, I get a 24i minus 12i squared. Then two things happen. I combine my lateral aspects and I get plus 18i. And for these, I'm going to get 12. That's 12 times -1. That's going to be a plus 12, which is going to be a 24. My 18i is just going to hang out, not causing any sort of a ruckus right there. And so over here, we notice it's the same pattern. I have a 2 plus some complex aspect, 2 minus some complex aspect. So I bet you I'm going to end up back on the real axis. I get 4 minus 10i plus 10i minus 25i squared. My complex numbers cancel out. My I squared changes that. So that turns into minus 25 times -1. So that is just 4 plus 25, which gives me a 20 9. And so again, kind of what we're seeing here is we're seeing another aspect of what's going on. My 2 plus 5i in this case is 2, 1, 2, and then I go up 1, 2, 3, 4, 5, and then I go 2, 1, 2, 3, 4, 5. I notice that the real number trajectory, 2 by 2, is going to give me a 4. And then I notice that the lateral trajectory, because they cancel each other out, rotates itself. And I get that result right here, and I end up at 29. But again, we'll get more into these mechanics at a later date. But there we go. So today what we're going to be going over is the third part of the quadratic formula. And now all of these are all going to have lateral roots. What that means is the fact that when we have our quadratic graphed, we're going to be graphing a quadratic that doesn't actually touch the axis. And we notice that what happens is the fact that we know that these actually don't touch the x-axis somewhere we can see. The problem is that we know the fact that with the math, we're going to get two roots. That's going to be the square root of some negative number, which means I'm going to have two answers that pop up somewhere. And what we notice is the fact that these two answers are going to be behind or in front of the x-axis. They're going to be on the lateral axis. So if we take our graph and we rotate it, and I rotate our previous graph right here, but in this case, I give it a front and a back. So instead of having an xy, I have my x and my y, and I've rotated the graph out. What we know is that this graph is going to have two roots in the x-axis way back here, which in essence means that this is going to be more like a tunnel or a slide. So let's go ahead and see the true shape of a quadratic by looking at some of these lateral roots. Okay. So first off, we know that with any quadratic, using the quadratic formula, I'm going to identify my a, my b, and my c. And I'm going to take it, plug it into the quadratic equation, negative b over 2a, which is my vertex. And I'm going to add the distance to one root, which is the square root of b squared minus 4ac. We also call that discriminant. So that's going to give me my root on the right. And then I'm going to also take it away, which is going to be my root on my left. And so let's go ahead and plug this in and see what exactly happens. Oop, tried to fill in an a there. Awesome. So here, I know my b is 2. My a is 1. Oop, that's a 1. My b is 2 and 2. My a is 1 and 1. My c is 5. And let's start working this out. So I have a negative 2 plus or minus, well, that's a 4. Negative 4 times 1 is negative 4 times 5 is negative 20. 2 times 1 is 2. And so you already see a problem of brewing right here. X equals negative 2 plus or minus the square root of negative 16 all over 2. And the problem that we run into right here is if the square root of negative 16, if that were only a negative 1 and a 16, we'd be able to do it. So the square root of negative 1 is I. The square root of 16 is 4, which means this is actually 4i. So we're going to rewrite this as x equals negative 2 plus or minus our 4i all divided by 2. I know I can divide both of those by 2. It's negative 1 plus or minus 2i. There we go. We know the fact that it's going to cross the lateral axis 1, 2i, and 1 and negative 2i. Perfect. So let's go ahead and take a look at the next one. Remember, the first thing we're always going to do is identify our A, our B, and our C. And we're going to plug it into the quadratic formula, which consists of the vertex, which is negative b over 2a, And for 1, I'm going to find the distance to the left root, which means I'm going to subtract the discriminant, which is b squared minus 4ac. And then I'm going to find the distance to the right root, which means I'm going to add that. So I get my two roots by adding and subtracting the distance to the root from the vertex. There we go. And so all we're going to do is we're going to plug in my b, which is 2, my a, which is 1, and my c, which is 17. Let's see how this works. We have 2 plus or minus, that's a 4. 4 times negative, or negative 4 times 1 is negative 4 times 17. Let's see, 17 times 2 is 34. It's going to be a minus 68. So again, your first clue that this is going to be lateral is you see that this is about to be a negative number, which you know means it won't actually hit the graph on the real axis. And so now we notice that the negative 64, if I could only break that down into a negative 1 and a 64, I could root both of these. I know that this is an I, and I know this is an 8. So I could use 8i. Let's rewrite this instead of square root of negative 64 as an 8i. There we go. And again, we can reduce this by saying both of these divide by 2. Perfect. There we go. And so now, what I want you to try and do is I want you to try number 5, pause the video, resume it when you're done, and see how you did. Okay, so let's take a look. I have my A, my B, and my C. Plug it into my formula. My B is 2, my A is 2, and my C is 5. As I work this out, negative 2 plus or minus 4. Let's see, that's 8 times 5 is minus 40. Again, we notice that this is going to end up being negative, so I know it's going to hit laterally. Square root of negative 36. I know that negative 36, if I break that down into a negative 1 and a 36, I can square root both of those perfectly. I and 6, or just 6i. So we get x equals negative 2 plus or minus 6i all over 4. Now this I can't fully reduce, but I can divide all three numbers by 2. Which says x equals negative 1 plus or minus 3i all over 2, which if this was a radical, we'd just be done. But again, when we have lateral numbers, we want to split it into the real and the lateral aspect. So I'm just going to break these both down into negative 1/2 plus 3/2 I. So that way I know I go half a unit to the left on the axis, and I go forward 3/2 on the lateral axis. And that gives me what we call, I believe, rectangular form given complex numbers. So perfect. So how are we doing? Looks like we're doing pretty good. So let's give another shot at one of those. Now that you're a little familiar with how we break it down, see if you can't break this one down a little faster. I'm going to go ahead and pop the work on here. And let's see how you did. Now, one of the things you'll notice that I do is that often I go ahead and I write out the quadratic formula, even though many of us just go ahead and say, hey, I know what my A, my B, and my C is. They just plug it in. what you'll end up doing is by writing this out, A, you commit this to memory, B, one of the big mistakes is that you saw me do it, where you'll put the wrong letter in the wrong spot. This is a very easy formula where a lot of people make very simple mistakes. So I always recommend writing it out. And the good thing about that is that when you write it out, you'll catch little things like this. Where here my B is a -4. And by writing it out, boom, boom, I see that I have a double negative, which is going to turn that positive. One of the big common mistakes we talked about previously is that that -4 somehow keeps a negative because students see negative B. Well, my B is negative, so therefore that becomes -4. And that's an incorrect assumption that by writing the full thing out, you avoid it. A is 4 and my C is 5. So I'm just a big proponent of writing it out. So 4 plus or minus 16. Let's see, 4 times 5 is 20. -4 times 20 is -80, which again, we notice that it's going to hit laterally right here. -64. And so I think we're comfortable enough to notice that if I have a -64, I know that's going to give me an x equals 4 plus or minus. The real square root of 64 is 8. And because it's a negative, it's going to be 8i. So we're going to skip that middle step. If you don't feel comfortable skipping the middle step, don't worry about it. Include that. You can always write out -64, -1, 64, and then square root both of them. Get your I 8, which is 8i. You're always welcome to do this. Nothing against that. I can divide 4a and 8 by 4, which gives me 1 plus or minus 2i all over 2. I know I want to split this into the real and the lateral aspect, which brings me to x equals 1/2 plus or minus 2/2 I, which is really just saying x equals 1/2 plus or minus I. So now this one hits 1 on the right and then 1 forward on the lateral axis. And I guess the other one would be 1/2 and 1 backward on the lateral axis. Perfect. So let's take a look at this one. Last one. Pause the video, try this last one, resume it when you're done, and we'll see how you did. Okay, let's take a look. Plug it into our formula. My B is 2. My A is 5. My C is 10. 4. See, 4 times 5 is 20, times 10 is 200. I know that is -196. I know the square root of 196 is 14, which means that is -2 plus or minus. In this case, square root of 196 is 14 because it's negative. It's going to be 14i. I can divide the 3 of these by 2. And then I'm going to split it into a real, 1/5, and a lateral, which is 7/5 I. So I now go left on the x-axis by 1/5, and I go forward on the lateral axis by 7/5, and I go back on the lateral axis by 7/5, and I have my 2 roots. And there we go. So today we're going to be learning how to create an equation for a parallel line. Now, parallel lines at this level, we're looking at lines that have the same slope but different y-intercepts. This comes from the idea that if we have 2 lines with two different y-intercepts. Let's say I have a point here and a point here. Parallel lines meaning that they have the same slope. They're never going to touch. But now, if I were to move my y-intercept onto the same spot as the other one, now the rate of motion that it's crossing the axes is going to be the same, so those two lines are touching at every point. And now, if we had a third variable, those lines would be perfectly fine. They're two lines that are the same thing, but they're on top of each other. But at this level, parallel lines typically have the same slope, but different y-intercepts. So let's just assume they have to be different. So that's exactly what we're going to do. We're going to look at an equation, look at a point, and we're going to create a line that goes through that point, but is parallel to this. So that means we're going to need to create an equation in what we call point-slope form. Point-slope form is going to be the equation of y minus a y1 equals m times x minus an x1. And this tells us our three pieces of information that we're going to need. We're going to need to find a y-coordinate, an x-coordinate, and a slope, all of which is given to us in this information right here. So we're going to look and we're going to say, hey, I see that we have an x, I see that we have a y, actually we're going to call that x1 and y1. And then looking at this equation, I know this is in the form of y equals mx plus b, which means the number in front of the x is going to be our slope. And we can just plug that information in. So we can take the y1, which was our 8, our x1, which was our 2, and the slope, which was 3. And we can solve this equation just like that. Now, this is really only two steps. We need to distribute, which means we're going to multiply by that 3. Y minus 8 is 3x minus 6. And the last thing we're going to do is we're going to get rid of the constant over here to isolate our y variable. That's going to give us y equals 3x. 8 minus 6 is going to give us a 2. And we've created a new equation in slope-intercept form, y equals 3x plus 2. So we want to take an equation in point-slope form, plug in the information, and just solve for y, and that's all we're doing. So let's try another one like that. Let's take our equation of y minus y1 equals mx minus x1. And we're going to take all the information we see right here, our y1, our x1, and in this case, our slope is negative. So our y1 is a negative 7, our slope is a negative 15, and our x1 is a positive 13. And what you might notice is that we have a double negative right here. And those two negatives, when we have two negatives adjacent to each other, that's going to turn into a positive sign. So it's actually y plus 7. And then we're going to deal with the rest as we normally would. We're going to distribute that negative 15, which is going to be a negative 15x, negative 15 and negative 13. Let's see. 15 times 10 is going to be 150. 15 times 3 is 45. 150 and 45 is going to give us 195. Cool. And the last step is just to isolate the y by getting rid of that constant over there. It's going to cancel out, and we have y equals negative 15x plus 188. Boom. There we go. Easy enough. And so one of the questions you might ask is, well, does a fraction change how we're going to work it? And we always want to be careful with fractions because sometimes we may need to clear them. But for the most part, this one's going to work itself right out. So I have my y1, my m, and my x1. I have my x1, my y1, and my slope. So let's plug in this information and see what happens. So 16, negative 4, and 1/2. And so some of our eagle-eyes might notice the fact that we have plus a positive right here because I have two adjacent negative signs, which means that's really x plus 4. And here we go. Now, typically we'd like to clear this fraction, but in this case we notice that 4 can be taken in half. So 1/2 of 4 is going to be, well, half of 4 is 2. One of those is just 2. Half x plus 2. We notice that the half x doesn't change anything because we're just going to leave it as that 1/2 of x. The last thing we're going to do is get rid of that 16. So y is equal to 1/2 x plus 18. Here we go. So we see the fact that even with a fraction, it works out pretty well. So let's go ahead and let's try something with a slightly bigger fraction. How about 3/4? So y minus x minus. So you might say, okay, well, this is going to change a little bit about how we approach it. And for the most part, you are correct. We're not going to approach this 100% the same way, but the approach is pretty much the same thing. We're going to take our y1, our x1, and our slope, which is 3/4. Again, notice that we have two adjacent negative signs, which turns that into a plus 24. And we're going to distribute this 3/4. Now we recognize the fact that 3/4 of x, nothing crazy happens. We just leave it as 3/4 x. But this 3/4 of 24, we're going to break this into two parts. I'm breaking the 24 into fourths and then taking 3 of them. So let's actually look at this as two different pieces. Because a fraction, if I have 3/4 times 24, I'm saying, okay, take a fourth of 24 and then multiply whatever your answer is times 3. Actually, I should put that in parentheses so we don't think it's an x. So I'm going to take a fourth of 24. So if I break 24 into 4s, I get 6 of them. And I'm going to multiply that times 3, which is going to give me 18. So 3/4 of 24 is 18. The last step that we do is we're going to add the 16 over here to isolate our y variable. And so we get y equals 3/4 x plus 34. There we go. Now the last one, I'll leave these both on screen. On the last one, what I want you to do is this is a decimal. There's two ways to solve this. You can either try and convert this fraction to, or a decimal to a fraction and solve it that way, or you can see if you can't just work it with a decimal. So go ahead, pause the video, give a shot on number 9, unpause it when you're done, and see how well you did. We'll work both ways on screen. Okay, so let's see how well we did. So I have my equation of y minus y1 equals m times x minus x1. And I'm going to plug in my information of what I see directly in front of me. My y1 is a negative 15, my x1 is a 10, my slope is a negative 0.2. Now, if you did convert this to a fraction, what you'd notice is that the 2 is in what we call the tenths spot. So that's negative 2/10, or negative 1/5. If you did it this way, we're going to end up getting the same equivalent answer, but you're going to have your answer in fractions. So yours would look like y minus. You'd still have the negative 15 here, and you'd have a 10, but instead of having the negative 2/10, you'd have negative 1/5 because they're equivalent. Okay? In both cases, our first step would be to distribute. We have to distribute that decimal or that fraction to the inside terms. Oh, and let's not forget, we have adjacent negative signs. So if I have minus a negative, it's going to end up being plus a positive. Same here and same there. So y plus 15, y plus 15. So nothing changes right there. It's going to be negative 0.2x. And what we're going to see right here is we're taking 0.2 times 10. So I know that I'm just going to multiply the numbers. 2 times 10 is 20, and I'm going to add a decimal. So
20 with a decimal is just the number 2. Perfect. Over here, I'm going to do something very similar. I'm going to take negative 1/5 x, and I'm going to have to break that 10 into fifths. So if I break the 10 into fifths, that's 2. So negative 1 and negative gives me a positive 2. So in either case, I end up with the same constant on the outside. The only difference is what the slope looks like. And so our final step is we subtract the 15 on both of these things, which cancels out the 15 on the left, which isolates our y, equals negative 0.2x. 2 minus 15 is going to give me a negative 13. Y equals negative 1/5 x, and the same thing over here. 2 minus 15 is going to give me a negative 13. And so we see the fact that these answers are equivalent, even though one is a fraction, one is a decimal. And there we go.